so this is part 2 of this adventure. And okay, I got a lot of wink wink and nudge nudge, just say no more about the technical content of the first talk. You know what I mean? You know what I mean? Okay. But anyway, so I think this should be really, I'm very excited about this stuff. I mean, you can't tell. And, so I think we are in for a revolution. Let me start with the bombastic thing, okay? And really, we are in a fascinating time for physics, experimenting. I know that people are moaning and groaning, okay, because we're not seeing things. But if you think about it, for the first time, now we have probes on unprecedented levels of exploration of physical universe. Like, we never had a gravitational probe. Everyone thought it would fail. It didn't. It actually worked beautifully and giving us awesome stuff. We had cosmology probes, we asked astrophysics probe, underground experiments. The LHC might be seeing something new. There are people thinking about using probes which are non-accelerated probes for particle physics and interferometers, AMO probes, and so forth. This is a remarkable time. I also think it's a, when we think about what's happening with LIGO, this is going to be a renaissance in general relativity. I mean, there's no doubt about it, okay? But it's also a renaissance in quantum theory, okay? And partially, of course, it's been brewing for the last 20 years because quantum information, quantum computation, and so forth, people like you thinking hard about interpretational issues, so forth. And mathematicians, philosophers, physicists, they will unite in all these fronts. And I think finally this totally undefined and crazy subject called quantum gravity will come to something. And I think the usual expectation that quantum gravity is useful only, well, it appears on the Planck scale, okay, which when you talk to your colleagues in the physics department, tell them that, and they walk away. Planck scale, they were going to talk to me. Okay, this is simply false. Quantum gravity, the first thing that quantum gravity will have to explain is why there's this box. Why is there phenomenal space? Why is this big? At the same time, as I say, like quantum theory had to explain why this is hard. And it did. All exclusion principles, stability, and error. Okay, so this is what quantum gravity has to explain first. It doesn't have anything to do with Planck scale. Okay? So, but more, okay, it will have to tell us or teach us how to live with quantum theory. Because we don't know how to live with quantum theory. We constantly fudge. We want many worlds. The worlds are large. They're classical. So we want particles, classical constant. We want waves, classical constant, wave function, classical constant. It's all pregnant with classical concept of history. Okay? So we have to take the theory as it is, learn to live with it, and then have one quantum world, one quantum reality. Okay? So this sort of started. Laurent Friedel is a well-known researcher in quantum gravity. He's done a lot of stuff in loop quantum gravity. He's one of the pioneers of spin foam models, group field theory, all sorts of things. Okay, mathematics, mathematical physics, anything. Remarkable guy and a friend. And Rob Lee was on one of the first papers on D-branes. Like me, he was a student of Djordje. He was on the original paper of D-branes. And actually, if you look at Rob's thesis, it's about Dirac-Dornfeld action, how you get all of these, Young-Mills theories on the D-brane and so forth. Okay, so he was there from the beginning. And so the three of us, and plus I should write the paper maybe you would like because it's called Quantum Spaces and Modular, but I didn't write it here. So let me put it on this messy board over here. Now this is a paper that just appeared, put it on the archive. You know how physicists are. We never worry about publication. Put it in the archive and then we're happy. It's called Quantum Spaces and Modular. And it's really about quantum mechanics. And the surprising message that if you start with quantum mechanics and look at it with right eyes, first of all, you will find a very unusual representation of quantum mechanics we never cared about before. There seems to be what the Akira has been talking about all the time, instead of not realizing maybe the math. Okay? And that actually directly goes to string theory. In a particular form, which is not a space-time form, Okay, that's why we call it meta-string theory. Okay, and it's more like a basically telling you the strings are propagating or making not a geometry of space-time, but geometry of quantum theory. Okay, they're moving in something called modular spaces. Okay, and this came out from this very particular formulation that I will mention later. Okay, so if it gets technical, I will just basically say forget about it. Okay. All right, but I think you should try to philosophize. You should try to philosophize about F theory and so forth, but you should try to philosophize about the metastring theory because it has a cool name, meta. See, I grew up in Tito's Yugoslavia. You had to take 4 years of philosophy, even though I was in the math gymnasium, right? And philosophy basically went from the Greeks, very Western-oriented, and of course the peak is Marxism. And well, you don't know this? What's wrong with you? And then they told us, like, I don't know if this is the right story, but it's probably apocryphal. Someone was putting Aristotle's works, and there was Physica, and then Metaphysica is the book next to it. So that's why it's metaphysics or something, right? So, you know, we're writing the next book after Joe Polchinski's book, okay, or whatever. All right. Anyway, okay. So the world, so based a bunch of, it started in 2001. We were trying to make sense of a concept that came out from quantum gravity. Okay, and remember, one of the dichotomies that exist in this field, as you probably realize, you take string theory, it's like a big, whatever, elephant in the room. Whatever you call it, that breaks everything. There's all these other quantum gravity people over there. Right? And you know, they're talking about discreteness of space-time and quantum space-time. And these guys never talk about anything discrete, partially because supersymmetry doesn't allow you. You have moduli space, right? You just say moduli space. You can move any which way you want. Okay? So what is this? How can it be? All right? And so, but there's something that came out from that corner which was remarkable, right? It's a remarkable idea. And the idea had to do with the thing, it was proposed by Giovanni Nonino Camiglia, a bunch of friends, Jurek Kowalski Glickman, Lee Smolin, and Laurent Friedel. Okay, and it came out from various things, like Laurent came out from thinking about Reggie calculus, okay, three-dimensional gravity, putting some matter fields, integrating out the space-time and getting matter fields, some effective theory of matter fields, which look non-commutative, but kind of non-commutative in some phase space. And then I think for these guys like Lee and Jurek and Giovanni came out from double special relativity, okay? And basically the idea was somehow that, well, you know, quantum gravity might be not about space-time. And the intuition was somehow that, you know, it's maybe about this generalized relativity principle. That different observers, like in relativity, you say different observers see different space, and different time, and then you put them in space-time. Okay? Then you curve space-time, whatever, make it dynamical. Maybe here, what quantum gravity is telling us is that different observers see different space-times. And then now you have to put different space-times into something larger. Okay, I talked to Laurent about this, and in 2005 or whatever, we were writing some other paper on torsion and low quantum gravity, you know, like chiral fermions and low quantum gravity. But it took us a while to realize. But anyway, so each of us came from a sort of different angle with a different set of intuitions, and the obvious thing was when you think about, okay, what I'm going to put this space-times into? What's the larger thing? Well, you see. You know, when you actually measure in any particular space-time, what do you measure? You measure particular energies or momenta. You look at your particle going to the detector. You're not really, right, measuring space-time data. Usually you infer from energy and momentum data. They scatter, then you add the momenta, and you find the vertex where they maybe there was some interaction point and things like that, right? So you balance energy, balance momentum, because you appeal to the space-time symmetries and you get better charges, right? And you balance them, that's how you discover things, right? So the idea was for them, well, maybe we should put them in phase space, because you see there is like a space-time and there is a conjugate energy momentum space. And if you take all of these guys, the different observers see all the different space-times, you have all the different energy momentum space, you should put it in something which is like a phase space. But it's not a phase space of, let's say, gravitational field. Right, what you find in general relativity. It's a phase space of probes of the space-time. Okay, so this is a very probe or observer-dependent picture. Okay, if you think about quantum theory, I'm just trying to philosophize in a very poor way, physicist way. If you think about, I guess this is what we call philosophizing. You probably think it's just very sloppy. But anyway, so basically, if you think, I'm trying to make a bunch of intuitions, right? If you think about it from the point of view of quantum theory, we say, well, okay, maybe quantum theory is about a bunch of space-times, because the most naive thing I'm supposed to do is integrate over space-time metrics, correct? So maybe I should work with a bunch of space-times. But you see, there I'm committing, right, to a very particular entity, right, space-time metric. It's not clear is it a good variable. Yesterday I was trying to compare it to a sigma model field after one of the talks on asymptotic safety. And that's why people usually, when they hear about asymptotic safety, they say, chiral Lagranges don't work, they embed it in something larger. Right? So therefore, if really Einstein's theory is like chiral Lagrange, it's going to be embedded into something larger. The non-locality, which would be like graviton is a composite. Okay, that's why people are sort of skeptical. The argument is that you maybe a bunch of own, okay, but this is the gut feeling. They have a gut feeling, and you're going with this. Okay. Anyway, people should do other things because it's very genuine, good, non-perturbative quantum field theory. We always need to know. Coming back to this, so there's this relative locality, and of course they were thinking, oh, maybe particles or something. But see, if you think about relative locality, see, that would mean that, okay, in usual physics, all observers, right, would agree on what you mean by local. And that's why we can use local labels for, let's say, quantum fields. We have, in some sense, a concept of absolute locality. So you see, we are trying to imitate the big guy. Yeah. Albert sitting there in Bern, right, scratching his head and coming up with all these concepts, and we're trying to do this at perimeter. Okay, and saying like, well, is it like that? But you see, once you abandon locality, then you start freaking out. Because you see, the moment someone said, non-locality, right? I can't touch it. Why can't you touch it? Let me tell you, I had a discussion with Gerard Toft, great band, right? Original, right? And he says, why does he like non-locality? Not because of space. With spatial non-locality, you can live. But temporal is crazy. Because now you can start violating causality. Come back, kill your grandma, all this stuff. Okay? So this is why usually people freak out. Okay, about non-locality. But we should not. Okay? Sometimes, the worst fears are indicating like where we should go. This is like the Zen thing. Like, I'm afraid of this stuff. And actually, maybe this is where I should go. Freudian, right? Whatever. Right. and so, okay. So then you say, like, okay, so how do I make sense? Maybe relative locality is trying to make sense of this concept of non-locality because non-locality is so weird. We have examples of non-locality, and I will list them. But we were talking about string theory. String theory is, in some sense, for me, the only example of a working, pragmatic, technological approach to non-locality because these guys have a scale. The string's supposed to have a scale, right? L string, the size of the string. But somehow we do it something different. We turn it into conformal field theories, but again, work on local things on world sheets and so forth. But generically, they're non-local. Right? I mean, T-duality will not exist without them not being local. Okay? So there is some technology there, a non-locality that we have in string theory. There is this conceptual new idea that came out from quantum gravity. Okay, can we put the technology, okay? We call it the oracle. So the string is the big oracle. Put stuff in, comes out. Okay, but you have to know what to put in. Okay, so can you put some new concept? Okay, like relative locality and get something new. That was the origin in 2011. Okay, of trying to think about this, and it's still continuing right, to this day. And all of this stuff I'm saying, it's basically we never expected this. We're sort of, should I call it discoveries or should I call it? Something came out and something new. All right.
When you say the relative non-locality, it's really whether two events occur at the space-time point.
Yeah.
Because when you say non-locality, philosophers are really familiar with Bell non-locality.
Okay, so I will try to clarify these things.
Okay.
Because I think even though we're giving, that's a great thing, because realizing, understanding EPR, both Einstein-Podolsky-Rosen, and of course Schrödinger, and then David Bohm with his spin realization, and of course Bell. This was great insight before the crowd, okay? And then experimental is doing this. But you know what? It's only kinematic. It's only kinematic on the locality. I'm talking about dynamical, and I think the insight of Aharonov there is even stronger. No one listen to Yaki. I mean, it's kind of hard to listen because you don't understand what he's talking about, right? But it's interesting, like to see someone who is 84 years old but 24 in his mind. We all want to be like that. Anyway, so okay, so let's go through this. Okay, so where do we? I mean, we are so afraid of non-locality. Okay, so where do we find it anywhere? Yes, sir. So the world, as we know it, is fundamentally quantum. This is the learning. How do we learn to live with the quantum? Okay, we are afraid. Okay, so why? Well, you see, this is the message, right, that Yahir is trying to propagate. Okay, the quantum theory is essentially a non-local theory which is consistent with causality. So it's not Newtonian non-locality. It's not only spatial non-locality. It's spatial-temporal non-locality. But it does not violate causality. Okay. Now, okay, by causality, let's say in the context of quantum field theory, you take you take operators, space-like separated points, and that commutator, let's say. Now you might question it and say, like, hey, you're advocating something purely quantum, but you're using this crutch, which is classical causality. I will come back to that idea that maybe there is causality. I think people, as you know, in quantum information, we talk about this, right? Are there sort of extensions? If you really want to live and be fully quantum, okay, is causality a classical this Swedish guy doesn't like. I love Bergman, okay? Love me back. Verloten, or whatever. All right. So basically, this is the big message, and then they say, how do you encapsulate this message? You see, most of the usual representations will not encapsulate this message because you see, they always rely on something classical. We're going to be measurements, or whatever here, or there is environment interacting, but it's, you see, these are always classical variables around. I think Yahir's point was, can we isolate purely quantum variables with no classical limit? They don't exist if you take h bar goes to 0. They're not there. And then, can we observe them? How do we observe them? Okay, so this is what he calls modular variables. I'll try to explain what he calls it. Now, you have probably heard about a Aharonov-Bohm variable, right? You do a double slit experiment with an electron, right? You stick in a magnetic field between those two slits, right? And then you see the shift in the experiment interference pattern, which goes exponent I over h bar, maybe E over C or something like this. Basically, the flux. Okay, that's called like that's a uniform magnetic field. Seen everywhere. Comes metaphysics. In mesoscopic physics, they take a wire, they make a loop, they take a wire, they put a magnetic through a field, and they see electrons. They can measure, in the lab, they can do a double slit experiment. There's a dual of this, by the way. And when I purchased the book of Aharonov, I guess 10 years ago, when did it come out? Aharonov rolling book. Look at it, please. Look at it. Quantum Paradoxes book. And I learned about this dual phase that I didn't know, and I told a condensmatter colleague, and he became obsessed ever since. We wrote some papers about it. Aharonov-Kasher phase is also observed. What do you do with that? Actually, I should say Anandan Aharonov-Kasher, because Jivanandan also apparently independently came with this concept. But basically, take a double slit experiment, shoot neutrons. Well, these are not charged, but they have spin. So how would you see deflection? You can't do magnetic field, but you can do electric field. Because as you know, the spin will couple with the electric field. I mean, you can spin orbit coupling if you want. The magnetic moment across the electric field will be the relevant. Integrate that over the holonomy, that will give you the phase. Okay, now of course, because it's electric field, magnetic field, there's some 1/c² factors, suppression, and so forth, as you know. But again, it was measured. Neutron interference experiment, you know, they observed the Harman Kardashev phase. It's harder to observe in materials, okay? And that's why quantum matter people are interested. You can even think about, oh, there's sort of states of matter like quantum Hall effect that utilize not the Aharonov bomb, but the Aharonov Kasher. We've written papers about this, but no one has seen it in the lab yet. Some of my friends are looking at it. Anyway. Okay, so this is, you see, as I said, quantum non-locality consistent with causality, so the quantum field theory is possible. Because you say, like, hey, you know, we know the local quantum field theory works. There's Paul Stainer model, we use local quantum field theory in condensed matter, critical points of the statistical mechanics, immensely successful. And I'm sure some of you philosophize about it, correct? Okay, there's a whole Wilsonian paradigm, right? That's based, crucially based on locality. So you see, it's this is possible. So you have somehow you have this non-locality cannot be of a Newtonian or any arbitrary type. Okay, that's why it has to be consistent with causality. So particular variables, and then we have to understand what kind of measurements. Maybe I'll mention this towards the end, though. Depending on what time I have. Let's see. When did I start?
Shortly after 11.
So let's say 11:05. So I have 12:05 will be an hour, and then 20 minutes discussion or something like that. Okay. Anyway, so then, you know, as Nick pointed out, well, there is one, when I guess philosophers like to think in terms of non-locality in the context of entanglement. But I'm going to be talking about non-locality of interference, because that's a more dynamical non-locality than this one. This one is more kinematic. Okay? And this one, I think, goes to the heart of the matter. Okay, so then there's this issue of space-time. Okay, special theory of relativity. All right, definitely that defines the concept of locality, introduces the notion of causality and all of that stuff. But you see, the natural outgrowth of special theory of relativity, if you want to engage it, right, you make a general theory of relativity, exhibits non-locality. Right? Because, you know, to define GR observables, one thing that you learn from loop quantum gravity, everyone should learn, right, in string theories, right, is that basically you take this connection, what are the observables, the holonomies of the connection, exponent of the holonomic connection, there is some G Newton there because of the measures of the connection. That's the unavoidable loop. That's what you should work with. It's like the QCD I told you about, right, that we don't know. Right? Here's your non-local string-like variables in your face. Okay? So definitely we work with non-local observables. And then there's this issue of asymptotity. We were talking about this background independence and so forth, right? I mean, all right, so someone is telling you, right, that here I'm in the Sitter space, supposedly. Put the scale here. I get on the scale. I read some, I don't want to read what I'm reading. Okay, it's too much. Okay, but obviously because of equivalence principle, I don't care if I'm in Gödel universe. The scale will read the same. However, if you ask me as a mathematical relativist to produce for you the formula for the weight, mass, and whatever local gravitational field, in the Sitter space, given the Sitter asymptotopy, well, I've written papers with Vijay Balasubramanian and the board where we suggested that formula, but I don't think mathematical relativists have that formula. Okay, if you write it in asymptotically flat space-time, you can maybe write it in this anti-de Sitter, but you don't know how to do it in the Sitter and parallel in this space. Not to mention, you know, Gödel universe. So there's that issue of that non-locality, right? Okay. So basically what we would like to understand is sort of non-locality in quantum theory and general theory of relativity, and basically our statement would be that this harks back to the foundational aspects of quantum theory in the context of space-time, quantum space-time physics, which we call modular space-time, boring. Modular from quantum theory, from Aharonov, but you'll see why modular appears. And then metastring theory in the sense that meta, you know, this is sort of a theory from which the Polyakov string or anything that I talked about yesterday would be a singular limit of. Okay. All right, so let's take model variables of quantum theory. So we go to the two-slit experiment. Many people have said, if we understand two-slit experiment, we're fine. I think if you talk to David Djordje in many world, if he says like, if you understand two-slit experiment, just photons, you're fine. I'm happy. Okay, if you talk to Feynman or anyone, yeah, If you understand two-slit experiment, you're fine. All right, let's understand two-slit experiment. So the usual story is we work with Schrödinger. Okay, he saved the day, right, because he gave us these intuitions, but I think he also misled us a great deal. He gave us a great equation, which is great for quantum chemistry and things like that, material science and whatnot, but conceptually it could be misleading. So the question that Aharonov says is, what quantum observables capture the interference without relying on the Schrödinger picture? Has anyone seen the wave function? I am. She's saying like this. I think it's like ether. You see, there's always this thing like, you know, yeah, right? Something is so natural. Of course, anything is natural, right? Communism was very natural for me because I grew up in a communist family. You come here, it's weird. These Americans weird? Did they never heard about communism? However, you know, I meet a guy on Broadway, right? I remember, actually, my friend had this experience even before me. He came here as an exchange student in the mid-'80s. And then, you know, there was a guy on Broadway trying to persuade him, right? He was visiting New York, says, just get a bunch of Bibles into your country. Once they read it, there will be a revolution. They come out. You see? Anything can be in your mind. You can believe that something is there, but it's not. Right? That's why we have to cross-check each other and so forth. And, okay, so the question that Aharonov was saying, like, okay, so this might be really a classical intuition, right? And so how about we go to quantum observables, right? And think in sort of this Born-Heisenberg, Born-Heisenberg-Jordan picture. So start with Born-Heisenberg-Jordan commutation relations and start, okay, so if we are talking about, let's say, an electron going 3, and you have whatever distance between these two slits, which is r, well, can we construct some observable in terms of these q's and p's that is going to capture exactly this phase? That's what he's asking. It's a technical question. Well, you can persuade yourself there's a no polynomial function of q and p that will work. Okay? Well, however, okay, if you take an exponent of Rp, I over h bar, of course you know this is a shift operator, this is a translation operator. You take the undergraduate in quantum mechanics, c to the I over h bar, Rp, acting in the state, psi of x is going to shift it to psi of x plus r. Right? So if you have the translation operator, there's no problem. Okay, but you see, if you have a translation operator, you see, in some sense, immediately you start talking about something modular or periodic, because the argument of an exponent is defined up to 2 pi, you know, n. Okay? So I'm going to use Aharonov's notation, but I'm going to write here on the board, actually, and you can find it in this Quantum Spaces of Modular paper. And when did I put the eraser? I had it, and it fell. All right, so I'll just basically write it maybe more properly mathematically, but this is how he writes it in the book, so you don't have to don't get confused. All right. Oh, I wrote the. So this is the FLM paper, right? All right, and so basically what he says is, okay, so let me define some new variables that take into account, right, this modularity, the fact that this operator is a phase. You see, but I could have written an operator like this. Okay, so let's call it U. Yes.
Can you use the blue pen?
Can I use the blue pen? Yes, sir. I can do that for you. For small fee. I'm joking. All right. So U equals. So we write this guy, which is the exponent, right? Of I over h bar. And there is, how do they, well, it doesn't matter, like PR, right? And I'm going to write V, which is the exponent, well, the other guy, I over h bar, I could write Q, but you see, okay, here's your, well, not really T-duality, but just quantum mechanics, what happens on a complex space. If I had a complex space, obviously, the dual of it would be 2 pi h bar over r. Correct? So suppose now I take these two guys and I look at the commutator of U and V. And of course, I know what the commutator of Q and P is. This is the famous formula that's on Max Born's brain in Göttingen. Except I think it's written PQ in Göttingen, and then he writes it over I or something. It's an interesting thing that he did it in the flipped way. And instead of minus I, he writes it 1 over I. That's a good way. Okay, so this is the, so you plug it in, right? And anyone can compute this. This is the undergraduate in quantum mechanics. And of course, you will just basically, you know, you compute this, but the commutator is just going to give you an IH bar. And cancel, you get basically to the I over H bar, 2 pi H bar, so you do it. So it's 1, so UV is equal to VU, so it's 0. They commute. However, if I ask you to compute the Poisson bracket of these guys, UV, I mean in the sense like, take a P, take a Q, take a Poisson bracket UV equals 1. Never know. Didn't you learn somewhere in quantum in some textbook they told you the commuting variables, right? It's always classical, and there's more classical. It's not true. I just showed you. Isn't that amazing that, I'll actually tell you that some of these things go way back to the origins of quantum theory. Okay? The mathematics of it will go after World War II with Djordje Mackey at Harvard doing this. And then Aharonov resurrecting. These things have been with us from the beginning. Okay? In particular, Schrödinger recovering from one of the tubercular attacks in, I think, 1922 in Switzerland somewhere. Maybe he basically tried to understand Weil's theory. Remember Weil theory, the extension of general relativity with this conformal transformation? I was writing this for the world sheet, okay, but Weil was doing it in 4 dimensions. And instead of writing e to the some factor which is positive, like phi or something, he just continued. He wrote I phi. And instead of that phi, he was taking phi as a potential, like electrostatic potential. Or if you want, you can take an integral of a vector potential around the circle. And then he says, like, well, suppose I apply this to Bohr's 1922, 1 year before Bohr. De Broglie. Independent in Switzerland. And he, of course, if you take now periodicity of I over H bar, right around, you're going to basically find out it's a standing phase wave on a circular orbit. And you will get Bohr quantization condition. Being a mathematical physicist and conservative, he left it. Insane. Okay, so this is how phases, by the way, came first into quantum theory. Okay, the Schrödinger, and then of course the Broglie. Then I'll show you something from 1924 and more. This was all before Heisenberg's later, not to mention Schrödinger. All right, so now you see, instead of writing this using these, which was proper, this is what mathematicians would do. Right? It's like algebra to the group, right? You take these exponentials and you see you write it like that. Okay, so what Aharonov says in the book is he takes the, right, this modular vector. So P is basically defined mode 2 by H bar, which is basically the same thing over here. Right? And Q is defined mode R, and then he writes this puzzling relation. You might say, like, oh, by the way, how did he do this? Right? Which is, of course, this relation. Then it's trivial, right? To compute this one. Okay, and that this just basically means that Q is defined Q modulo plus NQ of R, and P is defined P modulo plus NP of 2 by H bar. Now notice that the H bar goes to 0 and something singular happens. As a matter of fact, in this particular case, even cancels, right? So it's right. So it's a pure phase. These are pure phases, and you might say, like, you see, this is precisely what we don't detect with when we want to do wave functions, right? But these pure phases capture this phase. Okay? It's all about these phases. It's all that's the essence of interference, right? But now written in operatorial language. Now look at this. Because U and P commute, or these Q and P commute, you can actually, in the sense of a 2 pi H bar area size on a QP phase space, you can actually localize them in a 2 pi H bar area because they commute. However, you don't know in which cell they are because there's this NQs and NPs. They don't commute with Qs, the modular Qs and modular Ps, or if you want with these U's and Ps. So in other words, uncertainty principle is contained in the fact that even though you know where you see, You can put them, localize them in a cell. Usually you say the cell is fast. No, it's not. For these guys, it's not because they commute. But you don't know in what cell they are. Okay? All right, finally. Okay, this is the point that actually Haronov wrote in the original paper, 1969. But I will tell you, he didn't know this. And I don't think he listened to me when I told him. But anyway, so this was actually written by Born in 1924. And the first paper, I think, that has quantum mechanics in the title. Even though someone told me that Carl Hertzberg, who was a student of Zondervan, delivered lectures in Munich in 1919, where he used the word quantum mechanics. You know, Hertzberg then came to Baltimore. Anyway, so I don't know if this is true. Okay, but definitely I know this is true because you can look at Born's paper and it says on quantum mechanics. So, and so what I'm saying in this particular context is, let's use these variables and write just Heisenberg equations of motion for them. So you see they are exponents of something. So if you were to take a Heisenberg equation of motion, you would have to take a d of the exponent. I'm writing what Haronov wrote, but you would write the following way. You take a du over dt, you take a commutator of h with u. Correct? But you see, u, right, is just a shift operator, e to the IH bar rp. So anytime it acts on a function of v, it shifts it. I mean, a function of q. So therefore, you will get a v of q plus r, I just symmetrize it, minus v of q over r. And of course, this is just written over here in such a way. This is written in such a way, so it looks, right, a discretization of what you would write for a classical Hamilton's equation. This is what Born did. You see, Heisenberg's paper, 1925, is built on two gentlemen, okay? One was his postdoctoral advisor, Max Born. One was his colleague in Copenhagen, Kramers, okay? A bold jump within Bohr's philosophy. That's that paper. Actually, even the notation in the paper, you can trace to Kramers' dispersion theory that Born tried to understand. Okay, you know dispersion. The idea was like, how do you quantum mechanically understand dispersion? You have a classical form goes 1 over frequency minus the resonance, and then Kramers just guessed there is the minus extra part, absorptive and emission part. And that's basically the origin quantity. Once you have that formula, it's in your face. But of course, you have to be Heisenberg to see this. And in particular, Heisenberg used this. You see what Born did with this Kramers guess. He said, oh, you know what's happening? You just write classical equations of motion in phase space. Okay, in his case, he didn't write with q's and p's. He worked with action and angle variables. And remember, action variable really has the units of action, right? And angle variable is dimensionless, right? So he wrote the action angle variables, if you look at the 1924 paper, and then he discretized them. He took just, you know, every time he would see a derivative with respect to action, he would take a difference and divide by h bar. I mean, in this case, of course, I have, because this is a function of q, I have to take a difference by some whatever variable, right? That's in this case, you know, experiment dependent, right? And then divide by it. If you take that Born correspondence principle, Born, okay, and Heisenberg did in 1925 paper, apply Bohr-Sommerfeld quantization. Integral PdQ equals 2 pi h bar. You know what you get? Of course, Heisenberg never wrote this in the paper. The origin of this is this type of equation applied to sort of a semi-classical usual phase. We say integral PdQ is an integer of h bar because it's a phase. Oh my God, what ironies of history. Okay, so anyway, so, you know, it doesn't quote Born or anything like this, but we want to write a tribute to Born, because you'll see Born will come back and back, and he's one of those guys who are totally neglected, partially because he was mathematically minded and not very, personality was not very, how should I say, engaging or whatever, right? Just the opposite. He has some personal problems and whatnot, so, but I think he's one of the heroes on science. Anyway, okay, so, now the claim of FOM is modular variables are natural in quantum gravity via metastring theory. As a matter of fact, metastring lives in a modular space, and it will naturally produce this. You will see why in a second. I mean, I can maybe tell you now that in string theory, right, you have these observables, right? And these observables are called sometimes vertex operators. Okay? So where do they come from? Well, if you study these two-dimensional conformal field theory, right, these will be the ones that have the correct transformation properties on the scale. Okay? And so, but you can understand them very easily. You see, from the string point of view, you have a, right, you want to pinch, right, the roll shift, right, to get into sort of scattering states. Well, there's a delta function type of things, right, in momentum. If you write the delta function as, you know, in the Fourier decomposition, what do you get? E to the ikx. You just integrate with the x and you get a momentum. Correct? So that's why they appear. Take this versus this. Okay? These operators are sort of staring in our, they've been there from the beginning, except now I have to explain, you know, this x is not going to be space-time x, but it will be something which we call double x, and we'll have to do with this duality in a second. Okay. So the first thing, as I said, is, okay, sharpen the concept of non-locality as relative locality, and I talked a little bit about this. To repeat again, absolute locality in the sense of quantum field theory, or special theory relativity, general relativity, everything in physics, constant in space-time, and independent of the nature of the probe used. In other words, it's some block, and you live with it. Someone gave it to you, right? Why? Isn't that sort of against the spirit of relativity? Because if you want really relativity, Einstein, you would say like, well, the constant space-time depends on the nature of the probe use, and in particular, all probes are quantum, on the quantum nature of the probe. You know, what kind of energy does this have? What kind of momentum does it have? Is it a point-like probe, or is it an extended probe? What are you throwing? Because otherwise, space-time doesn't really tell me anything. I listen. Usually it's silent. Okay? So basically the idea that the slogan, this is what goes as for, yeah, this is like philosophy, right? Different observers of different spacetimes. This is the big idea. See, one thing that in string theory that bothers maybe you, right? Especially when you study special theory, relativity, general relativity, right? You say like, wow, these are conceptual theories. It's so beautiful, right? I give you some concept, everything follows. Give you some mathematics, boom. Okay? Quantum theory does bother you because you're not sure what the constants are. String theory should bother you a lot, right? Because, you know, it's just this invention of techniques and so forth. You never know what the hell is the big picture behind it. So we want definitely to say that this is the organizing principle of string theory and quantum gravity. Okay? And so space-time is relative to energy momentum in phase space. So I will basically have some phase space, and I will slice it along certain directions, exactly like you have a space-time, right? You have a space-time, and you take space-like slice and time-like slice. Now I'm going to take a phase space of these probes, and I'm going to have space-time-like slice and energy momentum time slice. Energy momentum-like slice. See, it's a complete analogy. All right? Except everything is covariant. Space-time-like slice, energy momentum, or momentum energy-like slice. This is a covariant phase space. You might say like, well, that's not what I learned from classical mechanics. But you should know that actually there are techniques which are completely covariant techniques in phase space. They've been known since Schwinger, many people have used them, including string theories like Witten string theory. So general relativity people can use it. Right? But remember, this is a phase space of probes. Don't think about phase space of general relativity or fields or something like this. Okay, this is a crucial thing. Yes?
So, I mean, in the special relativity case, the different space-like and time-like lines or hypersurfaces, we get them related by Lorentz transformations, which are related to the laws.
Coming.
Okay.
Coming. So exactly like Nick says. All right, if you're saying this thing, what's the geometry? What are the things that relate things, okay? Okay, what's the geometry? What are the invariants? Okay, can we do Minkowski now? Okay, we did Einstein. Philosophy. Now we're going to do the mathematics. Minkowski. Huh? All right. So, but again, tribute to Born. In 1930s, when people didn't know, they knew zilch about quantum field theory. They were totally confused. Of course, in some sense, you might say like Dirac, Heisenberg, Dirac, Djordje. I guess Djordje is on some here or there. Djordje, Dirac, Heisenberg, and Pauli, they really set the stage for what happened later with Feynman, Schwinger, and all these people relativistic, manifestly covariant quantum field theory, right? And we know these days, I think if you look at Weinberg, he does the computation as it could have been done, totally non-relativistically, right? In the last chapter, if you want line shift, you can do it like Heisenberg, Pauli, no big deal, once you understand what's going on, right? But at that time, people were confused, right? They wanted next revolution, right? They just had one. Immediately, they're like Leon Trotsky, never stops. Okay, and so, but it stops. It's like it stops. Maybe it will come in 100 years. So anyway, so Born thought of this, right? Well, he says like, look, I'm a mathematically minded person, right? Remember, he was a student of working Minkowski, Hilbert, and so he's always more mathematical. That's why this physicist guy's isolated. See, sometimes matters what community you come from, which is horrible, right? It's like chauvinism, nationalism, intellectual. Anyway, so basically he said like, look, I mean, I take the QP equals IH bar, I take the Heisenberg equations of motions, what we call Heisenberg equations, or Djordje equations of motion, or Hamilton's equation of motion, or whatever, and you know, we see obvious duality. Here's a duality, we call it Born reciprocity. It's in the sense of electromagnetic duality. You take, you know, Einstein, Maxwell's equations, E goes to P, P goes to minus E, that's a symmetry, okay? So I can do this, and Born noticed this. There's a beautiful exchange between Pauli and Born about this, because Pauli, in his great wisdom, but being conservative, never committing to paper, a letter is okay, because who's going to read letters? Maybe philosophers, right, but no one else. Historians of science, I'm sorry. Too many philosophy jokes, man. I don't know what's going on with me today. Must be that coffee. Anyway, so basically, what Pauli said. Look, H bar is a composite. I mean, the units of the action, Q times P. Any future theory will have to take these two apart. Yeah? In other words, the dimensions of H bar, right? It's lambda times epsilon. There is some length scale, and there is some energy or momentum scale. So therefore, you should work with lambda and epsilon set. Okay? That's precisely what Born is saying. And then, of course, Born says like, well, you know what? This is interesting, right? Because in general, the X is curved. Space-time, right? And of course, I'm taking into account also the energy momentum duality, which is obviously not of this kind. And, but therefore, that means P is curved. So he already in the 30s talked about the prediction of this point of view. Curved energy momentum space. All right? It's interesting, there's literature on this involving people like, inventors of supersymmetry, Golfan, he wrote about this. Many other people have written, Yukawa and so forth, Lande. It's interesting, it's a bizarre literature there. I found 200 references to the review of Born. And of course, no one pays attention to this because it's like, well, I don't know what that is. But basically, this would be the statement. And this is where Pauli told him, hey, wait a second. Because you have to worry about causality once you start doing these things. You will get non-locality. Okay, and then you have to worry about causality. It's amazing insight. This guy is very smart. All right, so now basically what I want to tell you is about this geometry of relative locality. Okay, so let's try to imitate Minkowski. So to unify space-time with energy-momentum space, so remember everything covariant, space-time, energy-momentum space, in phase space of these probes. We work with probes. And by the way, when you tell string theory is this, they say, I know this. It was always about probes. That's where we differ from GR people. Because for us, space-time really doesn't exist. It's not an arena. It's all with probes, and maybe probes make it in some relation, whatever. Yeah. So you don't tell me anything new, but we do. So basically, we need both the fundamental length scale and fundamental energy scale because I have to make some. I have to measure this with a stick, and I have to measure this with some other stick. Yeah? So this is this Pauli comment, right? And therefore, in principle, well, what I need to do is, you see, apart from considering products like this, the other possibility is this. In 4 dimensions, this is just G Newton. But I will call it alpha prime. And this will be my interpretation, or now re-understanding of what alpha prime is. So I'm not going to give it the space-time interpretation directly. I'm going to give it this interpretation in which you see you work with two scales. That means now when you start organizing physics, if you're effective field theorists, you are not going to have just one UV cutoff and then decoupling between high energy and low energy physics. No, you will have a UV and an IR cutoff, in principle. I'm not sure if decoupling will happen. This is, again, there will be a sort of remnant of non-locality. I'll tell you some of these things actually happen in non-commutative field theory, except there you violate Moran's. Okay, so I'm going to define some quantities, right, which are basically dimensionless, okay, and these dimensionless quantities I'm going to put together because I'm working with phase space. In some sense, this guy came from Q, this guy came from P, except they're dimensionless. And their commutators now properly, if I take the H bars and so forth, the Poisson bracket like this, and the commutator is operates like this. But that's basically this. Okay? Now this phase space has three natural structures that live on it. The first one is a symplectic structure in the covariant sense. So if you went into some local coordinates, double coordinates, what you would write is omega AB. This is an anti-symmetric tensor, right? Two-index object, and it's just basically dp wedge dq, where this is covariant, so therefore there is also E and T. Okay? Okay, it's a phase space, right? Then it has a generalized quantum metric. You can think of it that this comes from Born's rule, if you were to think about in the Schrödinger representation you want to assign probabilities. Because Born rule is basically a measure. It's a metric. Alright? So again, we're defining it here. It's a symmetric tensor, okay? The signature is 2, 2, d minus 1, right? Because you see, I'm worrying about causality here, which is another thing that in string theory you don't worry about. Let's say if you're quantum gravity side, this is a big thing that you worry about. Causal, that's what it is about. You will see that they will come. Yes.
Chris, I
thought you wanted me to follow you. All right. So here is the signature 2, 2. But you see, one signature here is for time, the other signature is for energy. Okay, it's not 2 time. Okay. Notice it's a conformal group, right? Because now it's an SO 2, 2d minus 1. This is a conformal group. Like this is what you basically see in ADS CFT, right? You see SO 4, 2. It's always 2. Like remember conformal group, you get basically Flomer lines, right? You just basically add one temporal and one spatial. SO 3, 1, you add 3, 1, 2, 3, and 1, 2, 1, and then you get SO 4, 2. So it's a conformal group. Okay, so this metric you see, it looks like this: dq squared over dt squared is over dq. This is covariant plus gnp squared. And now you say, like, well, why don't I see this metric? Well, this is precisely where the weakness of gravity, another puzzle. Why is gravity weak? All right, because of the weakness of gravity, we see only the dq squared part, in other words, space-time metric. But it doesn't mean that the other part doesn't exist. In other words, space-time is thick in the energy momentum directions of these probes. Okay?
Those sixes, it's because there's 3 space dimensions?
Sorry?
The sixes that appear in your metric. That's because there's 3 space dimensions?
No. Look, I mean, everything is d-dimensional, right? So everything, right? So it's...
Why 6 then?
Where 6?
Yeah.
Oh, this is G Newton. Sorry.
Oh!
This is G Newton. This is G Newton. G Newton, G Newton, G Newton. Right?
Okay.
Remember Belushi, right? Can I have an omelet? It says, no, cheeseburger. Can I, right? It says cheeseburger, cheeseburger, cheeseburger. It's G Newton. G Newton, G Newton, G Newton. And Pepsi. All right. So, okay, so this is, so basically gravitational tension, if you want, if you take a c squared over G Newton, is large. Okay, so space-time, this is an interesting thing. See, I will have to construct space-time to you and then tell you, like, why is it big in principle, and why can't you cut it? I can cut my arm. I can. One matter interacting with the other. There's quantum mechanics explaining why I have a shape. Right? It's quantum mechanics that is explaining this. Right? Why things are hard. Stability plus the Pauli exclusion principle. So we have to have an explanation why space-time is like that, but it's also non-cuttable. Why is it a blob? Okay, and then we have a polarization metric, which is the analog of causal structure. So here is the analog of Minkowski. Here we have a stuff that we didn't have, but that's because it's a phase space, right? And we have a sort of a mirror image of the anti-symmetric tensor, but now it's a symmetric tensor. Okay, it's just a dp/dq. This guy tells us what is space-time like and what is energy momentum like. You see, he has an ODD signature. By the way, I'm talking about quantum mechanics, but some of you who know T-duality reference is something, you know, that group also appears when we talk about ODD, but I'm just talking about relative locality. Flat eta fast would mean absolute locality. All right? And okay, so now you can go mathematical. Vector tangents to space-time, and now with respect to this eta, exactly how you would define things. Let's say space-like and time-like in space-time. So now you did space-time-like, energy momentum-like. Okay, so you have what mathematicians would call bi-Lagrangian structure. Lagrangian is manifold is always basically take an omega symplectic form, evaluate it, it's equal to 0. And if you talk to mathematicians, they think of phase space in terms of Lagrangian manifolds. I think Einstein from Berkeley has everything is a Lagrangian. Right? Mathematicians, for mathematicians, this is it. Here the structure naturally appears. Okay, so let me shift the geometry of quantization. Okay, so quantum theory really is about the phase space and these three structures. Okay? The polarization metric defines the splitting of space-time, phase space into space-time / momentum energy. And there is a subject in mathematics which tries to take into account this structure. Now it's becoming maybe a little bit tough for you, but there's a subject in mathematics which takes into account this structure. This structure would be then called a generalized metric. It's just a subject of mathematics. Basically what you do is, instead of thinking about manifolds from a differential geometry point of view, where you take a base and then the fiber, you sort of double the fiber. Okay. The reason for this really came out from string theory, I think. Okay, but then mathematicians just abstracted it. There are some issues there, and I would like to say that actually what they are doing is just a special case of this geometry, which we like to call Born geometry. Okay, so in the context of that generalized geometry, right, where they have a generalized metric, eta is just completely fixed. Okay? Now remember symplectic forms, your classical mechanics, like it looks like 0, 1, minus 1, 0, correct? But this guy, eta, is symmetric. It's 0, 1, 1, 0. Okay, symmetric complement to these symplectic. All right. Okay, so now I want to talk about the new, again, we're introducing constant new concepts here. There will be new words. Modular space-time, metastring theory, Born geometry. Now I'm going to introduce a word called gravitizing quantum theory. When you introduce a new word these days, you go to Google, that's the oracle, plug it in, see if someone else has done it. And of course, there is one gentleman. Penrose introduced a concept like this, but in a completely different context. You remember he's warning about quantum measurement, he wants to collapse the wave function, he still thinks about wave function, and he thinks gravity can do something to it. So he wants to gravitize the quantum, of course. With the mind. All right. Great thing still. Okay, in quantum theory, basically eta is arbitrary. You can change polarization, you can go from Q to P. That's like what we were talking about, change of basis. We call this Born duality from this point of view, but of course you would just call it change of basis. H is flat. This is just Born rule for probability. These are the measures of it. Okay? In general relativity, eta is fixed. You always have a fixed basis in general relativity. You always measure in space-time. This is the problem, this is the dichotomy between general relativity and quantum theory. I can give you any basis in quantum theory you can measure. This is the problem of the pointer basis. Like people, how do I select the basis? I can always go to some other crazy one. Okay? But in general relativity, it's fixed. Okay? It's a space-time basis and flat. However, if you take this double metric, restrict it only what you call space-time, that means the Lagrangian, that means the Einsteinian G mu, it's curved, it's dynamic, that's the GR. So in quantum gravity, you see what we're doing? In quantum gravity, all of these have to be dynamic. As a matter of fact, omega as well. The symplectic structure gives rise to how you define dynamics. It should be dynamic as well. Here we're just writing this too, but omega also comes in. Okay? All of this that you have, right? Like Minkowski geometry becomes dynamical. The whole triple becomes dynamical. All right. So now I'm emphasizing this because there's two strategies. Like either you quantize gravity, that's relative locality and curved energy momentum space are predictions. Like because I have eta AB, which is now dynamical, that's relative locality, and I have HAB, which is now dynamical, but on this sort of phase space. So therefore, I don't have just curved space-time, but curved energy momentum space. Here are predictions of quantum gravity. Do I talk Planckian? No. I'll tell you more. Two strategies now. Either quantize gravity, which what everyone does. Okay, you take a metric and turn it into an operator, whatever your favorite thing is, or you were thinking about the wave function of the universe, I don't care. Do some quantization. But you're not touching data. But here I'm telling you can do the opposite. Mess with data. Okay? Don't have to touch H because it's flat. That's the Born rule. You're not changing it. So you would gravitize quantum theory. Presumably they are the same. String theorists would say, maybe this is philosophy now because we gravitas. You invent the words, what does it mean and so forth. So I have to give you some meaning. Okay, dynamical phase space geometry. This then implies dynamical phase space geometry, which is the dynamical geometry of quantization. And basically, in quantization, you can understand this omega AB as symplectic structure of phase space. Eta AB is what they call symplectic connection in the context of deformation quantization. Essentially defines how you determine operator order. Okay, and then this guy, HAB, essentially defines what you mean by I in the Schrödinger picture, the complex structure, and this leads to another way of quantization, which is totally different from this one, which is geometric quantization, and that leads to Hilbert spaces. And these are just now special cases. Okay, I'm just relating to what you know. Okay, so now you might say, like, that's a great story and so forth, you know, but when you do special theory relativity, you write a relativistic particle. Max Planck did it, like one of the first papers, or do something. Show me where this shows up. And then, you know, Minkowski rewrites the whole. Actually, yeah, I think it was Minkowski that Born-Sommerfeld. I think Minkowski who wrote the Maxwell theory. I think Djordje wrote the action E squared minus B squared, and then you write it FU. You write it fully covariant. So give me an example, okay, for this whole thing. An example is a formulation of string theory. By the way, this did exist in the literature, in particular Arkady Tsetlin in the late 80s and early 90s when people were worrying about T-duality in string theory, trying to sort of give a worldsheet description of it where T-duality would be manifest. Covariant. Okay? And so we sometimes call this Tsetlin action. This type of actions, which you will see, it's different. It looks like very radically different from what I wrote, the Polyakov action. It would entail, first of all, this phase space variables, x and epsilon. Remember, there was a lambda and there was an epsilon. These type of actions appear in different contexts when you want to do what's called chiral bosons. Okay, so this is a technical context. You know, we don't have chiral fermions. The question is, can we have chiral bosons? And people struggle to write actions for it and so forth. The issues are sometimes that they are anomalous and whatever, some technical things. But anyway, look how the action works. It's very similar to Polyakov, and as a matter of fact, it comes out from Polyakov. So if you look at one of our first papers, I'm not going to bother you with this. There is a step. You can go from Polyakov, okay, rewrite Polyakov in phase space, split sort of the phase space into sort of x and x tilde, rewrite that, and you get this guy. One thing that Tsetlin omitted is this term, okay? And that term is usually omitted because it looks like a boundary term. That actually is quite important. So, you see, the action is, I write it in terms of tau and sigma, so it doesn't look manifestly Lorentz covariant with respect to worldsheet. Tau and sigma now split. So you can't say T-duality is just an exchange of tau and sigma. That will not work, okay? It's chiral, okay? Because you see, you know, I have a sigma term, and tau sigma don't have a del tau x if you want square term. It has a phase space structure. If you think about your PQ dot, this would be like this, and this looks like a Hamiltonian. If you know anything about quantum Hall effect, Okay, if you know about quantum Hall effect, there's a rewriting of a Chern-Simons theory from the point of view of the boundary excitations, and exactly has this form. This eta would then, in the quantum Hall case, be called the K matrix. They usually drop omega, and this term they call a dirty term. It's a term that comes from material, whatever, non-universal things. There's lots of structure here, lots of physics, lots of intuitions that you can appeal to, but it's a little bit technical. Okay, so how do you, but what I'm saying is that eta, omega, and h appear. And now this is your, once you plug it into string theory is going to treat all of these guys, in a quantum case, as couplings. You will write beta function equations for these guys. You will have generalizations of Einstein's equations. And these equations will know about the geometry of quantum theory. And actually the space in which this is now living doesn't have anything to do with space-time. Space-time, some slice. It's like you said, like, okay, I'm Newtonian. I like my space and absolute time. Well, tough, because we live in phase space. And different observers have different space-times. And I can relate to them with this geometry. Exactly how I do with Minkowski. Okay? So, and this is the theory that realizes it. Now you might say, like, is it a unique theory, blah, 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 and so forth. And as a matter of fact, as I said, I treat it as an oracle because at the end of the day, I will get the structure of this space, which will not be target space in the sense of space-time. It will be this quantum space out of I'm going to build everything. That's the idea. Even including strings. I will build space and time, including and strings, anything. So that's why I meant that. This is just an oracle. It's a machine because of this beautiful technology that I have, that I can put all of these things, stick it in, and get something out of it, right? Because I have the technology, whereas otherwise maybe I would be lost. Yes, please. Okay, so so there are some technical parts here, so maybe I'll just skip and go to modular space. Yes.
Okay, so you said different observers see it.
Yes.
You mean because they're using different probes?
Yes. So the crucial thing here is it's a probe dependent. It's a probe dependent picture. You're basically building everything out of probes. But you see, now you are ending up with this. Okay, so there is some 2 beta function equation, double RG. Also, you can recover Polyakov. It's chiral. Okay, one thing that I think it's great is that you derive non-commutativity, fundamental covariant non-commutativity of this axis. You can just derive, and eta measures that. You can look at these vertex operators and so forth. It has some connection, beautiful mathematics of these, maybe you've heard about monster groups and things like that. So this appears. By the way, in mathematics, Djordje has considered this compactification of the bosonic string all the way down. But it's a real 25.1 string. So if you ask string theorists even who are interested in this, like write more work, a great paper, find it in this whole direction, you say, well, it doesn't make sense. Why? Because everything is compact. So therefore, time, and I'm going to go back, kill my grandmother, it doesn't make sense. This is the wrong picture. These are not compactifications. These are quantum spaces. And these are quantum spaces in the following sense. I will explain the last transparencies. If I give you spin, and I say that there is up and down that you measure in the Stern-Gerlach experiment, do you tell me that the rotational invariance is broken? Of course not. Because you can make a superposition of these 2 states and recover the whole sphere of rotations for anything. Correct? Why? Because it's a quantum object. So what I'm basically saying is that this toroidal, what people think is toroidal compactification, is a complete space-time prejudice. It is not correct. I mean, it is correct if you stick to the Polyakov picture. In this picture, okay, this is a singular limit, okay, of something that's totally quantum, and like the spin, rotates, completely consistent with Lorentz. Okay? Even though it has fundamental discreteness. And this modularity, if you want, compactness in all directions, in space and time. I love it. Okay, so this is the modular space. So how would you then think of space? All right, and time. Well, you can think of it algebraic. You see, everything is operatorial here, so it has to be algebraic. All right, and then we're going to recover geometry from algebra. If you want, this is the spirit of non-commutative geometry. It goes way back to Delphi, right? Basically, the space. Okay, so everything is in this Heisenberg algebra. Okay, but then you look at the commutative subalgebras of the Heisenberg algebra. Okay, this is a mathematical question. Mathematicians answered it. In the late 40s, early 50s, this is Djordje. Okay, he found out that all commutative subalgebras, or if you want to think about the group exponentially, it's all commutative subgroups of the Heisenberg group. Okay, are captured by integral self-dual lattices. These are the lattices that you basically get if you compactify, let's say, toroidal compactification of the string. They're sometimes called Narayan lattices. They don't have to do anything with the string. They're in the structure of quantum theory. Okay? Now what happens here, and this is now a view of why relative locality is needed, is that like in the spin, you see basically if you boost the lattice, okay, suppose I have my lattice, but you have yours, you boost it. Then what happens to our commutative subalgebras? They do not commute, right? Because they're embedded in this bigger Heisenberg thing. That means that I now take the superpositions of the states, exactly how I did with the spin. And therefore, even though these are discrete lattices, they have a lambda and epsilon. Okay? We are fine from the point of view of the Lorentz, like the spin is fine from the point of view of rotation. And what's the resolution physically? Well, for the spin, different observers are going to see different spins. I mean, different probability for spins in Sx, Sy, combinations or whatever. Relative locality is the resolution of the discreteness married to Lorentz. That's why relative locality is that different observers are going to now see different spacetimes. Okay, anyway, so again, new concepts. You see, you start now with these compact guys and you build spacetime through what we call extensification. Don't think about compactification. I think compactifications, all of these things, they're useful, okay, but physically they will never be realized. Okay, they're just, you see, they were grateful playground for exploring things that will be mathematically useful. But physically, if I think cosmological, okay, I'm building stuff. I'm evolving stuff. Okay? I'm not living in a classical spacetime and I'm compactifying to little fluff like you were saying, Calabi-Yau, and then, you know, I have a 4-dimensional spacetime. I'm building stuff. Okay? There are lessons here for quantum field theory. So quantum field theory should be now reformulated. There is still a boogeyman in quantum field theory, as you know, is that in quantum field theory, even though we are happy with the Solian formulation and so forth, we don't really understand the physical origins of normalization. It's all buried in space-time, which is treated as a classical index set. Now we're saying you should formulate it in terms of modular space-time, is using these. So we have to have a modular quantum field theory. Classical, whatever, quantum ordinary local quantum field theory is a singular limiter. Okay? There's issues about, you know, time is modular, causality, okay, let me not go. But anyway, so Metastring knows about quantum foundations. As a matter of fact, you know, if you really take this Aharonov thing, and I think now we have also removed contextuality from Aharonov, because people can complain, okay, what is this R in a Aharonov experiment? I do R like this, and you do it like this, and she's going to do an experiment that is different, so it's all contextual. In quantum gravity, there's lambda and epsilon. That's it. I remove contextuality. Contextuality would emerge once I extensify and get different experimental situations. Okay, I know that sometimes people say quantum gravity doesn't have anything to do with foundations, this is separate things and blah, 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 whatever. Here, I think, you're putting them together. And in between, you have to reformulate quantum field theory. Okay, there is a thing that I said is, see, there are new excitations of the metastring. For example, there are, in the closed string sector, gauge fields that carry both worldsheet and space-time indices. They were not allowed in the Polyakov string. There are, of course, new excitations because you don't have just doubling of the metric, but also this polarization metric. So if you look at the LIGO type of equations, weak gravitational, they're like this. Okay, so this is now, I think, the concluding thing. The outlook is, I think there is a physical principle behind string theory. Okay, the physical principle is relative locality. This principle is needed to reconcile the discreteness, the fundamental problem of quantum gravity, which is discreteness and Lorentz. By the way, there is a beautiful mathematical formula that we write in this paper, maybe you should see it. You know, when I grew up in the old country that's gone, we were always taught, right, Hegelian philosophy, maybe Hegels, right? Okay. Thesis, antithesis, and synthesis. Everything about triples. Here I'm living the world of triples. Now, of course, you come to America and you hear about Charles Saunders Peirce. He talked about object, subject, and interpretation or something like that. So we have triples. All right? Here are the triples, okay, of the symplectic. 3 is the magic number. Well, you tell me in logic, you know, Peirce had some statement about logic, but you teach me why triple is important in logic, because he had some statement that this is the fundamental thing about the logic. Okay, and he was, you know, not a yo-yo, right? Okay, so if you take the intersection of the symplectic, the O, D from D, and this other, right? Remember this was eta, this was omega, and this was H, right? Which is SO 2, 2 minus 1. You know what you get? Lorentz. If you take any pairwise intersection, you will get general linear, unitary, or OD cross OD. If you did not have the third, we invented the third. You know, like the person who invented the second actor. Like Greeks, like originally it was just there was one actor on the stilts, and it was in the monotone, there's scores. Then the big invention is inventing the second guy. 2 guys on stilts, talking to each other with a chorus. If you invent the third guy, you have politics. Because the 2 guys can go against the other, they can change alliances and so forth. You have a little city, you have a little state. Right? We have the third guy. Because if you take just 2, if you really forget the omega or something, you will never see Lorentz. You will be puzzled. You will think, like string theories do, usually in the particle formulation, compactifications break Lorentz. You live on a lattice, that's it. By the way, there was also a nice feature there that I missed, I guess, explaining is that there is a feature when you combine this eta and H, which is a chiral structure, which then maps the space onto the action is basically because this X goes into that J of X, J being eta minus 1 inverse of eta times H, and J squared scales to 1, and that's the explicit action of the duality. Okay, but that's just a technical thing if you care. All right, so I mentioned some things here about the real world, but maybe just leave this transparency that we have a discussion. Okay, because I think this is relevant for the real world. There are new excitations, so quantum field theory will not just have particles. It will have extended things. Okay, we'll have to find them. Okay, there's also left-right symmetric formulation, non-commutativity. I think maybe this is the reason why Alan Kohn is saying this rewriting of the standard model, you know, a non-commutative structure behind this. Okay, vacuum energy, well, now you have 2 scales, all of these issues related to vacuum energy, hierarchy, and so forth. So that's why in this causal picture, don't trust this, because you don't know why the space is big. By the way, why the space is big? Because these guys are incompressible. In the paper we showed that you would have to take a coherent sum of these guys, little module longs. Okay, and if you take a coherent sum of the one, in a particular sort of larger limit of that sum, you will basically get a classical space. That's the extensification. It's a coherent sum of quantum objects. Maximally coherent. They're maximally entangled. That's why you can't cut the space in 2. Okay? And the big space is big because this is compressible. This is like the stability of space, or if you want the Pauli exclusion principle for space. All right, anyway, I shall.
We have about 5 minutes.
Yes, please. Yeah.
Yeah, so I think you touched on this at the end, but one of the things we've been looking at this week is taking a theory of quantum gravity and taking appropriate approximations, finding semi-classical states, and then taking some limit to get back something that looks like general relativity. How does the story go here?
So the interesting thing here is out of this modular space you can construct both gauge fields. Okay, this is something that we haven't put out. But essentially you can see like this. Maybe I give you a simple illustration. So Px dot, right, that you would be basically writing for the usual phase-space action, and then I don't know, you would write, I don't know, for the Hamiltonian P minus A if it's coupled to the gauge field square, correct? Up to some halves. Suppose I do a canonical transformation of P, and I call this P squared. Okay, so what I've done here is I shifted the P by P minus A, and what I basically get is a Px dot, and then the coupling, right, which is just the Ax dot, which is the usual coupling with the gauge field. Turns out, pretty much anything, except the fermions. Gravity, gauge field, U1, non-U can come out in this construction. So you see, basically, quantum space, modular space, through its deformations, okay, can lead to the fields that you usually find at low energy. These are precisely the massless excitation of the orbital of the string, which, by the way, lives in this modular space. Okay? And it's very tempting, and we give some arguments that matter excitations are really excitations of this space. Okay, so, you know, okay, but as you know, everything is in details. So you have to. And the bar, technical bar in string theory.
Did you have in mind what you had to get back to the field equation?
Yes.
Something that looks more like. So yeah,
in the extensification limit with these wiggles, you would really get, you know, the mass. You would get Einsteinian structure, or you would get, for example, a structure that's dictated by gauge invariance, Young rules. So you would really get them. But you see, I don't want to talk about states and things like that because this is all operatorial, right? Because I think, you see, Schrödinger representation is also a singular limit of this. And you can go from the modular representation to Schrödinger representation with something which is called a Zach transform. It's known in mathematics and known in information theory. It's basically, if you want to sample, think of Born equation, like you basically, right, that non-local equation is you write Heisenberg equation of motion like the classical equation, except it's discretized, right? That was the difference equation, right? This is what Born did, right? So it's like you're sampling. You're doing sampling, right, with this resolution R. So if you're thinking about the best sort of sampling that you can do in information theory, it involves this transform. That takes you from modular representation to Schrödinger representation. Schrödinger representation is highly singular. Partially, you see, it carries all this burden of classical thinking because the arguments of the Schrödinger wave functions are these classical things. They're, you know, this 3n-dimensional space or the x 3-dimensional space. It's all classical.
So, ask what you mean by singular. You use that.
Singular in the sense that it's not generic. In other words, you would have to do some very non-generic thing. You have to kind of fine-tune it, the limit to find it. By the way, and the person who really, you know, confused everyone about this is, of course, von Neumann. I guess they did the same things with hidden variables or other things. He's a smart person. He gives a very smart way of why would you stick, you stick to Schrödinger because everything is unitarily related to it. But if you look at his proof, it's like a sleight of hand. He does a projection. Okay, and that, you know, totally squishes any of this modular stuff. The funny thing is that actually when you say Stone von Neumann theorem, like in the math literature, this is like it's a big thing about quantum theory, you add Mackey, who was a student of Stone. But if you look at the essence of Mackey's work, even though he didn't present it this way, it's precisely this giving you a new representation. And this representation you can then relate to physical proposals of Aharonov. This is what was missing. So there's a mathematics behind Aharonov's proposal, and not just, you know, smart thinking about experiments and situations. That mathematics is this, what I was telling you, and that mathematics is realized in string theory. Of course, string theorists didn't know about it, right? Because they're in the space-time interpretation. Of course, we know that everything is supposed to be two-dimensional conformal field theory. And if you look at the big Metastring paper, right, we're just following rules of two-dimensional conformal field theory. We don't care, you know, right? It's that the two-dimensional conformal field theory is producing for us this modular stuff. Yes, please. Yeah.
So, when you were talking about the geometry of relative locality, you were saying that, in some sense, like the conception of space-time as like position space-time needs not to be privileged anymore. So you want,
Like in special theory relativity, you don't privilege any space or any time.
well, you don't privilege any particular time axis. That's right. But you want to go farther than that. You want to say like
Yeah. This is a full generalization of relativity.
position, momentum, or position, putting in terms of energy and momentum. You want those all to be like on an equal footing and to come out of phase space somehow.
Yes. And this phase space, really is, about the structure of quantum theory. So quantum theory gives you this structure because the probes are always quantum probes. Okay.
So I'm wondering how eventually we perceive position space. We don't like see energy momentum spaces. So I'm wondering how eventually
we do measure energy momentum. Like when a particle goes in a calorimeter, deposits energy. That's what these guys measure. We always measure energy and momentum. Then we deduce space-time data. I mean, think about how you see the photon goes and deposits energy, right? Then, of course, there's an interpret there. The energy is transformed into a pulse that goes down. Then you have to reconstruct this. That's why I say, like space-time. Anyone seen this? Like, measure
You
change.
missed Monday and Tuesday.
Okay. All right. Sorry.
It gets filled in.
Okay. All right.
I'm a sort of cognitive science.
Oh, okay. That was great. Okay, I saw it.
Well, okay, let's thank Djordje again.